Okay, so in this set of notes, we're going to be going over chapter 3.3 to 3.5. This video will be about chapter 3.3, and we'll be learning how to divide polynomials. So dividing polynomials is pretty similar to the long division approach that we learned in elementary school. So just to review, as I know it becomes kind of second nature to divide, and we forget about what these terms are even called. So in this example, I'm dividing 38 by 7. So our 38, that's called the dividend. 7 is the divisor, 5 is the quotient. And because 7 times 5 is 35, when I subtract that and I get 3, and then I'm putting 3 over my divisor, and then that's the remainder. So we have a process for going through our long division of polynomials, something that's a little bit different than when we're just dividing numbers. So we want to arrange the terms of both the dividend and the divisor in descending powers of any variable, meaning that if our polynomial was 3x cubed, plus x to the fourth plus x, we would want to arrange it so our powers are descending. So I would put the 4 first, the 3, and then I need to fill in this blank, and then my x. So this is just filling in the missing power. And then we're going to divide the first term in the dividend by the first term in the divisor. And then the result is going to be our first term, and then we're going to multiply every term in the divisor by that first term in the quotient, and then whatever that is, we're going to write that product beneath the dividend with like terms and line them up, which is like pretty much what we do with just like long division in numbers. And then we're going to subtract that, and then bring down the next term in the dividend and right next to the remainder that we got from subtracting, and we're going to form a new dividend. And then we're going to use this expression and repeat our process until basically our remainder can't be divided anymore. And this happens when the degree of the remainder, which is the highest exponent of the variable in the remainder, is less than the degree of the divisor. So we'll go ahead and do examples of this so you can see it in action and it makes more sense. Okay, so basically our division algorithm, applying these rules, is if f of x and d of x are polynomials with d of x not equal to 0, and the degree of d of x is less than or equal to the degree of f of x, and that's because we're not going to be dividing like x by x squared, because nothing times x squared equals x, then there exist unique polynomials qx and rx, where rx is either 0 or degree less than degree of dx, such that we have our f of x, and we're dividing f of x by d of x, and then our result is q of x, and then this is like our remainder. Or we could think about this as f of x equals our dx times qx, and then plus rx, our remainder. And these are equivalent because we can essentially multiply this by d of x, and then we would multiply this by d of x, and we would cancel that d of x, cancel this d of x, and then q of x would be multiplied by d of x, essentially. Get rid of all these things. Alright, so like f of x is our dividend, d of x is our divisor, q of x is the quotient, rx is the remainder. So if our remainder is 0, if our rx is 0, we would say that d of x divides evenly into f of x, and that dx and qx are factors of f of x. So we're going to go ahead and divide 4 minus 5x minus x squared plus 6x cubed by 3x minus 2. So the first step is that we're going to take our dividend and then we're going to do it in descending power. So I just basically rewrote it so it could be in descending power. And then now I could divide it by 3x minus 2. I tried to break down each of the steps, but I'll go through it here with you too. So our first term is 6x cubed. So we think, okay, 3 of x times what gives me 6x cubed. So we're dividing here, like in this step, 6x cubed divided by 3 of x, and that's 2x squared. So I put 2x squared, and I usually place them over the term that is similar in power. So now I'm going to multiply 2x squared times every term in my divisor. So I'm multiplying 2x squared times 3x minus 2. So I get 6x cubed minus 4x squared. So now I subtract that. What I need to be careful of though is when I subtract it, I make sure I put parentheses around this whole term, because essentially I'm distributing the minus, the subtraction to both of these terms, not just the 6x cubed. So I subtract 6x cubed minus x squared and 6x cubed minus 4x squared, and I get 3x squared. And then the next step is to bring down my negative 5x. So as you can see, like most of this is pretty similar to when you're doing it just with numbers, bringing down terms and everything. So now I think my second step here is to divide 3x squared, because that becomes like our new dividend, 3x squared minus 5x. So I'm dividing 3x squared divided by 3x, and I get x, so that's my term that I put up here. So then I multiply x times 3x minus 2, and I get 3x squared minus 2x. So that goes here, and then I subtract them, and make sure I put parentheses. And then when I subtract, I get negative 3x plus 4. And then I bring down, or I get negative 3x, sorry, and then I bring down the 4. And then now I think 3x, what goes into negative 3x? So essentially I'm dividing negative 3x by 3x, and I get negative 1. So then I move the negative 1 up here, and then I multiply, and I get negative 3x plus 2, and then I subtract, and then I get 2. So I have a remainder of 2. Therefore, I have 6x cubed minus x squared minus 5x plus 4 divided by 3x minus 2 equals the polynomial that I got up here, plus 2, which is my remainder, divided by the divisor. So it's the remainder over divisor. Or I could write it in like that other way that I had set up here, when it's just the dividend on one side of the equal sign. So I have, this is my dividend, and then I have my divisor, quotient, and then just my remainder. Okay, so our next example is going to be, let p of x equals 8x to the fourth plus 6x squared minus 3x plus 1. And d of x equals 2x squared minus x plus 2. So we want to find polynomials qx and rx such that p of x equals dx times qx plus rx. So essentially what we're doing is we're going to be dividing p of x by d of x to find our qx and rx, because that matches the form from our division algorithm, this one. Okay, so I'm dividing, and I make sure that it's in descending powers, and it is, but I am missing an x cubed between these two terms, so I add a plus 0x cubed. Okay, so I do the same thing as before. I think 8x fourth divided by 2x squared is what? And that's 4x squared, so I place the x squareds on top of each other. I multiply the 4x squared times 2x squared minus x plus 2, and then I subtract. And I'm subtracting the whole term. And I don't distribute it. I just keep it like that, just so you guys can see. And then if you guys did distribute it, the negatives would become like positives and positives would become negatives. So essentially these two terms are supposed to cancel. And then I get 4x cubed minus 2x squared minus 3x. And I think 4x cubed divided by 2x squared is 2x. Then I multiply 2x times my divisor. I get 4x cubed minus 2x squared plus 4x. And then I subtract those and I get negative 7x, and then I bring down the 1. And then we brought down this 2. So then I have negative 7x plus 1. So we could actually stop there because negative 7x plus 1, the x is a lesser degree than the divisor, 2x squared. So that's it. So negative 7x plus 1 is actually my remainder. So we can see here that q of x actually equals 4x squared plus 2x. And then our x equals negative 7x plus 1. And we can see that this is like our p of x here. This is our d of x, our qx, and then our rx. Okay, so that is long division of polynomials. We also have this other quick method of dividing polynomials called synthetic division. So this is a method if the divisor is of this form, x minus c. So it lets us just compute it faster. So we'll compare these two examples. So here we have long division, and we go through the whole process, and then we get 2x squared minus x minus 3 minus the remainder is like negative 4 over x minus 3. So with synthetic division, this is a little bit faster because we actually just, we take the coefficients of all the terms and we just deal with those. So for that, we would have like, this is our c. So our c is 3, so we just have 3. And then we actually just take these coefficients, the 2, negative 7x squared, just take that, and then the 0 from when we fill it in, and then 5. And then we actually just like bring down the 2, the first term, and then you're supposed to multiply 3 times 2, then you get 6, and then you add those terms. You do 3 times negative 1, and then you get negative 3 up here. You add those, and then 0 plus negative 3 is negative 3. You multiply negative 3 times 3, you get 9. Or actually you get negative 9. And then you add 5 minus 9, and then you get negative 4. And so you add those, and then whatever term the term you start with is going to be a degree less than the dividend term. So we started with 2x cubed. So our quotient is going to start with x squared. And this is our remainder. Is the last term. Alright, so that was just me quickly talking over that. But this is actually like our the rules or the steps for synthetic division here. So we're dividing by x minus c. So we arrange the polynomial descending powers with the 0 coefficient for any missing terms. We write c as the divisor for x minus c with like in a little box. And then we write the coefficients of the dividend, which is this. And then we just bring down the leading coefficient to the bottom row. And then we multiply by c, which is 3 here. And then we write it on the next column in the second row. So we did 3 times 1 is 3. And then we add the values in this new column. And then we write the sum in the bottom row. And then we repeat this series of multiplications and additions until all the columns are filled. And then our last, basically our last number is like our remainder. So this one is the remainder. And then we use the numbers in the last row to write the quotient. And so the degree of the first term of the quotient is 1 less than the degree of the first term of the dividend. and then the final value in the row is the remainder, and we write that over the divisor. So in this example, since we had x cubed, our quotient starts with x squared. Okay, let's go ahead and do an example. So we're going to use synthetic division to divide 5x cubed plus 6x plus 8 by x plus 2. So for the synthetic division, we established that it has to be in the form x minus c. So we could go ahead and change x plus 2 as x minus a negative 2. So that would be the same. These are equivalent to each other, but we just want to get like the x minus a c value. So our c is negative 2. Okay, so this is how we would set it up in long division, right? So we would have x plus 2 or x minus negative 2 divided by 5x cubed plus 0x squared. So we can't forget that we need to fill in the spaces, plus 6x plus 8. Okay, so we start with negative 2 in our box because that's our c value. And then we write down all the coefficients from here. And then we go ahead and bring down the 5. So then we multiply negative 2 times 5, and then we get negative 10. So now we add up the values in the second column. So we're adding 0 and negative 10, and we get negative 10. Now we multiply 2 times negative 10, and then we get 20. And then we add, again, we add that column. So we do 20 plus 6 is 26. Then we multiply 26 by negative 2, and we get negative 52. So we put that here, and then we add the column again, and then we get negative 44. So here, this is our final product. So we have the terms in like red are our quotient, and then remember the degree of the first term is 1 less than that of the dividend. So we started with x cubed, so it will be x squared. So we have 5x squared minus 10x plus 26. And then our remainder is this last term, and so we put it over our divisor. So we have 5x squared minus 10x plus 26 minus 44 over x plus 2. Okay, now we have some theorems to go over. So we have the remainder theorem and then the factor theorem. So the remainder theorem states that if the polynomial f of x is divided by x minus c, then the remainder is f of c. So here we have a little proof. So we have that f of x equals x minus c times qx plus r. And that's because this is our division algorithm, right? So we're dividing f of x by x minus c. And then q of x is our quotient and r is our remainder. So we're actually going to evaluate f at c. So we get f of c because we want to see what f of c is. So we get f of c equals c minus c because we're plugging in the c for x, q of c plus r, and I have f of c equals 0 times q of, that's supposed to be c, plus r. And so 0 times q of c is just 0, so that cancels. So I'm left with f of c equals r. So yes, it checks out. Alright, so here's an example. So given f of x equals x cubed minus 4x squared plus 5x plus 3, we're going to use the remainder theorem to find f of 2. So by the remainder theorem, if f of x is divided by x minus 2, then the remainder is f of 2, right? Because if the polynomial f of x is divided by x minus 2, so our f of x divided by x minus 2, so our c is 2. Then the remainder is f of c. So in this case, our f of c is 2. Alright, so that's why we're dividing by x minus 2, because our remainder is going to be f of 2. Alright, so go ahead and use synthetic division. So we have 2, and then we have all of our coefficients here, and then we go through it, and then we get 1 minus 2, 1, and 5. So the remainder is 5, so that's our value of f of 2. Alright, so for our factor theorem, let f of x be a polynomial. So c is a 0 of p if and only if, so that's what this means, if and only if, x minus c is a factor of f of x. So we'll go ahead and do a proof of that. So we have f of x equals x minus c q of x plus r. And then we have f of x equals x minus c q of x, and we could do plus f of c because we know the remainder is going to be f of c from our remainder theorem. Okay, so we start with our if f of c equals 0, which is our c is the 0 of p part, and we want to prove then x minus c is a factor of f of x. So if we have f of c equals 0, then we would have f of x equals x minus c times q of x. So yes, x minus c is a factor of f of x in this case. So if c is 0, then x minus c is a factor of f of x. The next way, so we proved this way, now we want to prove this way. So if x minus c is a factor of x, then we could say that f of x times x minus c times q of x, these are the factors. So now we replace x with c, and then we get f of c equals c minus c times q c, or q of c. So that's going to equal 0 times q of c, and that's 0. So our f of c equals 0. So if x minus c is a factor of f of x, then f of c equals 0. Okay, so for example, we're going to solve the equation 2x cubed minus 3x squared minus 11x plus 6 equals 0, given that 3 is a 0 that we know of that equation. So since 3 is a 0, that means that f of 3 equals 0, and by the factor theorem, x minus 3 is a factor of f of x. So we could actually divide our 2x cubed equation by 3 and find our other factors. So when we divide by 3, we get 2x cubed minus 3x squared minus 11x plus 6 equals x minus 3, which was our factor, our known 0 of 3. And then we get this from our synthetic division that we just did. So I have these two multiplied. So now I could factor this using our traditional method of factoring. So I do 2 times negative 2 is 4, and then 3 I leave here on the bottom. And I know 4 times negative 1 is negative 4, and 4 minus 1 is 3. So you guys need to be careful though, because I'm factoring when the coefficient isn't 1. We keep the 2x squared and negative 2 in here, and then we replace the x's by what we just found. So I have 2x squared plus 4x minus 2. I do factor by grouping. So I'm factoring these. So I get 2x minus 1, and then I get x plus 2. So these are our factored form of this equation. So now I know all my zeros. I have my 0, x equals 3, x equals 1/2, and x equals negative 2. Okay. So for this next example, I'm going to find a polynomial of degree 4 that has zeros, 3, 0, 1, 5, and a coefficient of x cubed is 6. So I know that these are factors by the factor theorem because I have my zeros. And remember, for negative 3, I'm doing x minus negative 3 here. And so my factors are x plus 3, because I just combined those. X minus 1, and x minus 5 is the breakdown of our polynomial. And so when we multiply all these out using the distributive property, I get x to the fourth minus 3x cubed minus 13x squared plus 15x. So here I have a polynomial of degree 4, so that satisfies that. But now I need my coefficient of x cubed to be 6. And here it's negative 3. So I just go ahead and multiply by 2. So I can do this because multiplication by a non-zero constant, in this case 2, it doesn't change the degree of f of x. It just changed the coefficients. So our zeros will be the same. So when I multiply by 2, I get 2x to the fourth minus 6x cubed minus 13x squared plus 30x. So that satisfies what I was trying to find. Alright, I'll see you in the next video going over chapter 3.4, real zeros of polynomials.